All right, I'm going to go over yesterday's homework first. And then some more properties today as well. So on here, we have. Does anyone else who needs the worksheet from yesterday? 1, 2, anyone else? Okay, the top part wasn't exactly the same as the two examples that we've done, but it was very similar idea. So again, if it is a tangent line, then it should be forming a right angle with the radius. On this one, it said, we don't know if it's tangent, and wanted you to identify whether it was a tangent line. So, just like if we knew it was tangent, we're able to use Pythagorean theorem to solve for missing sides. These two, you can use Pythagorean theorem to show that they are actually tangent lines. Now, I did see an issue with number one. All right, on number one, depending on how you read that, you may have got two different answers. So, when looking at the answer key in the book, they actually said this 41 applied to the whole thing. Now, if you read it that way, great. If you didn't, then you would have got a different answer. So on the first one, if you set this up, you would have had 41 squared equal to 9 squared plus 40 squared. So, doing each one of these separate. 40 squared is 1600. 9 squared is 81. 41 squared is 1681. And yes, those two are equal. Also, if you recognize this as the triple 9, 40, 41, that's all you really would have had to do to say, yes, it is a right triangle, and therefore that is a right angle, and therefore, yes, that is a tangent line. Now, if you didn't read it that way, and this is the issue I had with it, because notice every other time they label it showing that it's representing an entire piece. So if you look at it like, oh, that 41 is only for this outside piece, which is what I would have done, then that was 9, this would also been 9, so the whole thing would have been 50. Would it be a right triangle then? If we were to put in a different value there for that C value, would it still work out the same? No. Right here, this side would now work out to 2500. The side still would have came out to the same value, and then not equal anymore. That's now an obtuse triangle, and it would not be a right triangle. Therefore, it would not be tangent. All right. So again, little issue with that problem because they didn't have it labeled very accurately. So depending on how you looked at it, I would take it into those answers. On number 2, this one was labeled clearly. Now, didn't have to do a whole lot of work here either. Just like I said, you could recognize this as a triple. That one, you can recognize that it's not a triple. What's the triple that's very close to that? 5, 12, 13 is a triple, right? On here, we have 4, 12, 13. Well, 2 of those parts are the same as this triple. Could this be a right triangle? No. Because if I was to plug these two into Pythagorean theorem, I'd end up with a 5 over there. Since it's not the same, but they're whole numbers, it's not going to work. So I can just recognize that since this is not a triple, this is not a right triangle, and therefore it's not going to be a tangent. So there's also no. All right, on 3 and 4, both of these you have tangent lines coming from exterior points. So here we have the point W, over here we have the point A. But in each case, these two are going to be congruent, coming from the same exterior point to the points of tangency. In this case, P and Q. This one we had A was our common exterior point, and then our points of tangency were B and C. So those two had to be the same length. So for both 3 and 4, all we had to do was set up an equation so that they were equal. So we had 3x minus 6 equal to 10, x plus 10. Solve, so bring x across by subtracting, leaves us with 2x. Bring the 6 across by adding, that's 16. Divide by 2, and x should be 8. On the other side, and same thing for number 4, and 4x plus 2 equals 2x plus 8. Subtract the 2x from the side, it leaves us with 2x. Subtract 2, that leaves us with 6. Divide by 2, and x is 3. On number 5. Well, 5 and 6, same idea. In the directions, they said assume that we have tangent lines if they look like they're tangent. So that means that this is a right angle, and this is a right angle at F and Z. So since we have right triangles, we can use Pythagorean theorem. Now, for 5 and 6, again, you can use Pythagorean theorem. Do you have to? No, both of these are triples. So on this one, if you're using Pythagorean theorem, the setup would have looked like this. And I'm not going to go through the whole thing. I'm just going to show the setup. We had 17 squared equals 8 squared plus x squared. Now, the triple here, we had an 8 blank 17. What's the missing value? For that one? 8, 15, 17. So that missing value was 15. Now, if you went through Pythagorean theorem and actually solved that out, you would also get 15. Same thing on number 6. On number 6, you had 3 sides. This was one of our triples. Anybody know which triple that was? So we had 10, we had 24. Now those have a common factor. This is our 5, 12, 13. Same as up there, number 2. We could use this idea to find the missing piece. It's our 5, 12, 13, but doubled. And what's our missing piece? 26. Yeah, we just doubled those. It was our 10, 24, 26. Hey, could you use Pythagorean theorem? Yes, and it would have worked out. And if you were setting it up, I'm going to show the setup for it. I'm not going to go through the whole thing since it wasn't necessary. But yeah, if you set it up, that would be the correct setup. If you solve, you should have got the same thing. You should have got 26. 7 and 8. So we have circles inscribed into polygons, or better yet, polygons circumscribing circles. When polygons circumscribe circles, all the lines are tangents. And anytime we have tangent lines coming from the same exterior points, we have points that are equal in length from the same exterior point to their points of tangents. On here, they ask for 2 things: find x, find the perimeter. We could do the perimeter first because since all these values have an identical other side, we had 4, 9, and 13 were the 3 pieces from each of our exterior points. We could go ahead and add those 3 together and then double it. So 4 and 9 is 13, plus another 13 is 26. Double that, and we get 52. Now, if you didn't do it that way, we could have found all the individual pieces first. Again, if this top part is 4, then QU is also 4. If PT is 9, then PS is also 9. If SR is 13, then UR is also 13. And you could have added those all up individually. So we get 52. And for X, well, this piece we're saying is 9. So we could say 2X equals 9. Divide both sides by 2. So X must be 4.5. Those are the 2 answers they're looking for. On number 8, same idea. This time we have a quadrilateral going around the outside. So we have 4 values for the sides that get doubled. So we have 5, 13, 5, and 13. We add those up. 13 is 26, plus 5 and 5, that's 36. 36 doubled is 72 for our perimeter. Again, if you wanted to fill in all the missing pieces, you could. Again, they all had an identical side. approximate coming from the same exterior point. On this one, X was 13. And yeah, those are two answers that we're looking for. Any questions on the homework side? Okay. So get the other paper here for today. All right, so on the paper that I just passed out to you, everyone. All right, this is it. All right. So on this one. We have a couple of properties, yes. I didn't give you one. Sorry. Is there anyone else I missed? I think that's the same thing. That's the same thing. I have too many papers stacked up over here. I did give everyone one that said 10-6, right? Look at your papers, because I've had so many absences. 10-6, yes. Okay, so on this one that says 10-6, we have a couple of important ideas on the front. Now, the first one here, where it's our where we have an angle on the circle, is very similar to something we already did. We talked about inscribed angles a couple sections ago. Remember, we had an inscribed angle. The inscribed angle is equal to the, to half the intercepted arc. Same thing here. So we have these lines, they're intersecting on the circle. And since the intersection is on the circle, the angles are half of their intercepted arcs. So we have the first one, angle YTB is intersecting arc TU. So this angle is half of that arc. On the other side, XTB is intersecting the major arc going around the other side of the circle, and that angle is half of that arc. Now, These lines are something else that we haven't talked about. We do have a tangent there that we talked about yesterday, but we also have something called a secant. A secant, so this line here is a secant. A secant is a line that passes through a circle at exactly 2 places. It could be a line, it could be a ray, it could be a segment, but if it passes through a circle in 2 places, it's a secant. So you could also say, we learned about a chord earlier in the chapter. You could say that a chord is part of a secant. So if we're talking about this entire line, it's a secant. We're just talking from T to B, that'd be a chord. The secant passes through a circle. Now, on the other diagram, so looking at the diagram on this side, this one's new to us. Now, they write this a little bit differently than I would normally write it, but we have the idea here, measure angle 1 in this diagram is equal to the average of the 2 arcs that the vertical angles are intersecting. So we know that angle 1 and angle 2 are vertical angles, right? This angle here and this angle here are vertical angles. Since they're vertical angles, they are the same. Now, they each have their own arc. These arcs are 2 different measures. The intersection is not on the circle. If it was on, sorry, it's not on the center of the circle. If it was on the center of the circle, then each one of those angles would be the same as the intersection arc. Since it's just in the circle, but not on the center, it's going to be the average of the 2 intersected arcs. So we find the length of those 2, add together, divide by 2. They have it written this way. I normally write it a little bit different. So if I said interior angle equals I just say usually arc1 plus arc2 over 2. Again, it's the same idea. And we'll kind of sum up all these formulas at the end so that you have something that's easier to study from. But look at the examples down here. The first example, you have 30 degrees and 55 degrees. They took these 2 arcs, added them together, and then divided by 2. So 30 plus 55 is 85, divided by 2 is 42. That'd be for each of those 2 angles in the middle. On example 2, they gave us that the arc on the outside, this whole arc was 168. So that whole thing is 168 divided in half, and we get the measure of the angle, which is 84. Any questions on that part? All right, down here on the examples. So now, on the examples, we have a couple of arcs that are going to be used here. These 2 arcs are not the same measure. But what we do know is the same measure is, again, those 2 in the middle, those 2 vertical angles. So since those are the 2 arcs that they are intersecting, we're taking the average of those 2 arcs. So we have 40 plus 52 divided by 2. 40 plus 52 is 92. 92 divided by 2 is 46. Now, on number 2 over there, a little bit different. They gave us the angle. So we can plug it in like it's an equation as well. So I showed you earlier, I wrote it as an equation. I said interior angle equals arc1 plus arc2 over 2. Well, we know this arc is 28. We don't know this arc. I'm going to call that x for now. That's the one they want us to find. Plug them into the equation. The interior angle goes in. 45 equals 28 plus our unknown piece over 2. Now, from here, we have the 2. We're going to multiply that over to the other side to get out of the denominator. 2 times 45 is 90. Bring the 28 across by subtracting it. That leaves us with 62, and that'd be x. Now, on number 3. On number 3, that one, you have an angle, it's intercepting an arc. Oh, for that one, same idea. This whole arc is 220. So if that's 220, what 3? So that angle is on the circle. So an angle that's on the circle is what compared to the intercepted arc? Half. So this is going to be 110. 220 divided by 2. 110. Number 4. That one that gives us the angle instead. So if we have the angle, we can find the arc by doing what? Find by multiply. So here we divide by 2. Multiply by 2. We're doubling that. And so this is 74. The arc then is double that. 48. Then multiply it by 2. 4. All right, number 5. We're back dealing with the arcs and an angle in the middle of the circle. So we have these 2 arcs. We can figure out those interior angles by taking the average. Add them up. We have 90 plus 130 divided by 2. 90 and 130 gives us 220. 220 divided by 2 is 110. Is that our answer? Yeah. That 110 is these 2 vertical angles that are being intercepted by those 2 arcs, right? Or I said that kind of backwards. These 2 arcs were intercepted by these 2 angles. So those are 110. What's 5 going to be? 570. Yeah, it's 180. So here, any straight line has to add up to 180. So that's 110. Part next to it has to be 70. That's going to get total of 180. Again, and on any single line, it's going to be 180. Now, I heard you say 360 there for a second. 360, you could use that idea as well. In the circle, all of the arcs have to add up to 360, right? At the beginning of this problem, since I know these 2, I could have figured out what these 2 are together by subtracting those 2 pieces from 360. Would have given me 140 left over for these 2 arcs that aren't labeled combined. Take that 140, divide that by 2, and you get 70. So there is more than one way to do that problem as well. Number 6. Here we have 160. For that arc. Angle 6 is intercepting the other arc. Well, what is this arc going to be? What's the arc that I just highlighted? This is 160. The circle is 200. This arc is 200. Again, that's not our answer. They want the angle measure. But if we now know this arc is 200, this is 100. Again, there's going to be multiple ways that you can do these problems. The other way you can look at it, this is a tangent line. If I continue that tangent line on the other way, after that is 80. This is a straight line. The other half, subtract from 180 would be 100. So again, there's gonna be more and more ways that we can solve on all these problems because we can use different properties. Any questions there? Other side of that, so this was page 37. Go over to page 38. All right, for this one, now, changing the formula just a little bit. Notice they gave us 3 different examples. But there's essentially one equation that we're using here each time. All right. So on the last one, if we had the intersection inside of the circle, we added them and divide by 2. Here, in order to get the angle measure, we're going to have 2 arcs that are being intercepted. We're taking those 2 arcs, we're finding the difference, and then divide by 2. Instead of adding, we're subtracting. So on here, I'm going to go ahead and label these. So I'm highlighting the bigger arc here for a second on each of these. All right. So our equation here, we have the exterior angle this time is going to be equal to the big arc, so I'm capitalizing this, minus the little arc, or in lower cases. That's our equation that we're going to use each time on these problems. All right. So if it's on the outside of the circle, exterior angle is equal to the big arc minus the little arc divided by 2. And we're talking about the 2 arcs that are being intercepted. So sometimes there's more than 2 arcs in the circle there, but there's 2 that are being intercepted by the angle. Same thing here. 2 arcs are being intercepted, 2 arcs are being intercepted. You might have tangents, you might have secants, but you're always going to have 2 arcs. Now, down in this example, so we had 34, we had 18. To find the measure of that little angle, take those 2, subtract. So 34 minus 18, that gave us 16. 16 divided by 2 gives us 8. So let's do a few practice problems. Oops, I went too far. Hold on. So on here, again, we are taking, in order to find this angle, taking the 2 arcs, little arc, big arc. We're saying the big arc, 80, minus the little arc of 40, divided by 2. 80 minus 40 is 40, divided by 2 is 20. That's our answer for number 1. On number 2, same idea. All right, we have a big angle, we have the big arc, the little arc, and we're looking for the angle. So 60 minus 80 divided by 2. Now, there are times where it gets a little more challenging. Again, number 3, we're looking for this angle. But we only have the big arc. We don't have the little arc. How are we going to find the angle measure? All right, so first thing you have to do is 360 minus the 220. And that gives us what? Oops, I didn't mean to draw that line. Hold on. 140. So that's this arc right here. All right, that's that arc. It's not the final answer yet. In order to get the final answer, we still have to plug into our equation. So we got 220 and the 140. Those are the two pieces that we're plugging in the equation. We had to find an extra piece first. 220 minus 140, that's 80. 80 divided by 2 is 40. That's our answer to this angle. Over there, number 4. Again, a little bit different. What we're missing this time, what they want us to find, is the arc. So, again, we wrote it as an equation earlier, right? It was exterior angle is equal to the big arc minus the little arc divided by 2. So we're plugging in this time. We have 20 is the angle measure. The big arc we know. We don't know the little arc. And it's over 2. So first get 2 to the other side. Multiply 2 across, you get 40. That's 70. We gotta get that over to the other side, subtract it. This is a negative 30. At first, that's the same kind of odd, but this side still has a negative x. So either divide or multiply by a negative 1, and you get x is positive 30. Got that? All right, 5. This is the hardest type of problem that you're going to see on this paper. So, have that arc. We have this arc. And we have our angle. All right. There's only one piece labeled. The only thing labeled on this one is the angle. So, first, what are we trying to find? We're trying to find the piece that I highlighted in green or the piece that I highlighted in pink. All right, so why do we say pink? Because pink is the correct answer. Trying to find the piece that I highlighted in pink. Why? So how do we know that that was LN and this is an LN? My last class wanted to say that it was the green at first. Well, but this arc also ends with LN. So both these arcs end with LN. Why is it the little one that we're trying to find? All right, so this goes back to like the first section of this chapter. How do you label a minor arc compared to a major arc? Minor arc is less than 180, right? How do we know that we're dealing with the arc that's less than 180 in this case? It's a different way to label it. So if it's a major arc, you have to include 3 letters. So here, we don't have a third letter on this side right now. So since they only use 2 letters, it has to be in the minor arc. So first, we have to know what we're solving for. So here, we are solving for the minor arc LN. For the major arc, we still don't have any value over there. But it's no different than what we just did on the one above it. How do we get that missing piece before? So you guys told me that this was 140. How did you know that that was 140 on number 3? Yeah, the whole circle is 360. So we subtracted the 220 from 360 to get the 140. Well, same idea down here. We don't have a measure over there for x, but the whole circle has to be 360. On this side I have labeled in green, is going to be 360 minus x. But that might be. So now write our equation. Our equation, we have the exterior angle. So we have the 50 degrees equal to the big arc, and put parentheses around it. I know most of you guys are using pencil, so I'm gonna put parentheses on that part for right now. Minus the little arc. So at first glance, you're gonna look at it and be like, well, why do I have minus x and minus x twice? Well, it's because the big arc is 360 minus the little arc. So that's all going in for the big arc. The minus x at the end, that's because that is our minor arc. Yeah, big arc minus little arc. Now it's an equation we can solve. All right, like I said, this is the hardest type of problem that we'll have on this section. Now that we're to the solving steps, we have everything plugged in, get rid of the 2, multiply it over. What do we have on this side now? All right. On this side, so the 2's gone, but we can simplify the top a little bit. We got 360. We had negative x and negative x. So negative 1x and negative 1x combined together to give us 2x minus 2x. Again, keep solving, bring 360 across. We now have negative 260, negative 2x. And last step's going to be divide off that negative 2, gives us a positive 1/3. And that was our answer on this one. Now, could we call the other side x? Yes. It would change our equation a little bit. But the reason why I went ahead and labeled that piece as x was because that's what we wanted to solve for. You could write your equation in a couple different ways and still end up with the correct answer. If they want us to find the big side first, again, we could call that side x, could call that side 360 minus x. Once you solve, you've got your answer. All right. So again, different ways to do it. 6 is actually easy compared to what we just did. We have most of the arcs labeled. We're just missing one of the arcs. So we got the 110, the 100, the 80. All of them have to add up to 360. So the missing piece there is 70. So 100 minus 70 divided by 2. Compared to what we just did, that one was much easier. So 5 is the one that's more challenging. I wrote the assignment on the top of the board over there. Again, it is page 39. It's going to be that whole page 1 through 12. Now, like I said, the majority of these aren't too bad. It's this I found that's a little bit challenging. So the only ones that I like that on that page I'm giving for the assignment are the last 2. So on page 39, 11 and 12 are the 2 that are going to be challenging. 11 and 12. Other than that, they're not too bad. There's only 3 properties. If the angle is on the circle, it's half of the intercepted arc. If the angles are inside the circle, then the 2 vertical angles are the average of the 2 intercepted arcs. So add them divided by 2. If it's outside the circle, it's the difference divided by 2. Those are the 3 equations you're using. All right. Page 39, 1 through 12. All right.